Okay, so we're supposed to identify which of the 12 basic functions that are odd. So we talked about even and odd in a previous video. Something is even if you can plug in negative x and you get out the same thing as if you were to plug in positive x. Okay, so this first function, if you replace y with negative x like this is saying to do, does that match the original function when you haven't messed with it? Does that match x? Those aren't the same thing, right? They aren't equal. So this is not an even function. Okay. Oh, sorry. We're looking for odd though. Okay. So that's the definition of even. Definition of odd says if you plug in negative x is the same thing as if you multiplied the entire outside of the function by a negative sign. So here's our function of x. If I replace x with negative x, it looks like this. Just a quick, simple replacement. If I multiply the entire outside of the function, this entire thing by negative 1, then I get negative x. They're the same. So this is an odd function. Okay, but if you try to do that with the next one, if you plug in negative x and then square it, that's not the same thing as multiplying by negative x, negative 1, okay? Because if you square something, it makes it positive. But if you have the negative sign on the outside after you square, then it stays negative. So this one is actually even, it's not odd. Okay, but don't forget they could be neither. Okay, let's check C. If you plug in negative x in here, raise it to the third power, that equals the same thing as if you multiply the entire outside by negative. Because look, negative 2 to the third, think about what that is, okay? Negative 2 to the third is negative 2 times negative 2 times negative 2, so that makes negative 8, right? So negative x to the third, that's negative x times negative x times negative x. That is the same thing as if you were to multiply the outside by a negative. Okay, so you have to check each of those. A hint is that sine is even and that cosine is odd. Okay, so there's really just one more after I give away that one. Okay, the three functions that are decreasing on the interval negative infinity to 0. So graph these functions and then look only on this side of the graph where I've shaded. Because this is negative infinity way out here and this is x equals 0. So you're only looking at it over here to see where they're decreasing. So let's graph, let's do this one. This is what the graph will look like if you plug that in Desmos. From negative infinity to 0, it's actually going up, right? Read your graphs left to right, just like you read a book. This graph is going up as we read it left to right. We're looking for where it's decreasing. So 1 over x, that graph looks like this. That is going down as we read it from left to right on this side of the graph, on the negative infinity to 0 side. So there's one of them. One of those three functions is d. It's decreasing from on the left side of the y-axis. Three functions with no zeros. Look, all you have to do for this one is check to see if the graph crosses the x-axis. So the first graph crosses the x-axis. That's the 0 where it crosses. Y equals x squared, that touches at one point. It's tangent at x equals 0. So it does cross. So that has a 0. Y equals x to the third. That crosses. That has a 0. Y equals 1 over x. That graph, if you graph that in Desmos, looks something like this. Okay? That never crosses the x-axis, never touches. So this does not have a 0. So D is an example of something that doesn't have a 0. The four functions that do not have end behavior limit is it's supposed to be x approaches infinity. Okay, so that's just that's some calculus notation. I think the book actually does later on. What that's saying is, look at the graph going towards the right. Look at the x values as you get bigger and bigger. So you're looking for the graph that never stops increasing. So y equals x. If I'm looking at x values as we get bigger and bigger and bigger, my y values are never going to stop increasing. So this is one that has, oh wait, the ones that do not have end behavior. Sorry, A does have end behavior that it approaches infinity. The y values are always increasing as you read the graph from left to right. As you approach the positive infinity is what I should say. Okay, let me do another example because I kind of mucked that one up. So this one, it has end behavior of positive infinity, which means that as you read the graph going towards the right, the graph continues to increase. So we're looking for the ones that do not have that end behavior. Y over x, this one seems to be an answer for a lot of these. Look at the end behavior as we approach positive infinity. The y values are getting close to 0. They're not constantly increasing. So D is the first one I found that has this behavior, that it does not approach positive infinity.